Okay, in this lesson, we are going to evaluate the moment of inertia, which is the important parameter in mechanics, especially involving rotational and um, orbiting object. Okay, so in mechanics, we have learned about first Newton's law, F equal to ma. That means an object of mass m, if it accelerates, it experiences force. And this force can be calculated using F equal to ma. Alright, so in the rotational mechanics, if you have an object and it is rotated around a point, okay, so the rotation, if it is accelerating, if it has a rotational angular acceleration alpha, if it accelerate rotation in a circular form, it has a angular acceleration alpha, and then it experience torque. Okay, torque is the force which makes something rotated. So this torque and its relation to the angular acceleration is the moment of inertia. So this moment of inertia is analogous to the mass. That means if mass is the measure of inertia, that means if an object is inert to motion, so the mass is large. So similar to this, if the moment of inertia is large, so it resists to motion, it resists to rotate. So this is a resist to move forward in linear form, but this is the resistance of an object to rotate. Okay, so this moment of inertia is defined as the product of mass and the distance from the point of rotation. So it has mass, and this is m. It has mass m, and its distance from the rotational point. This is d. So that the dimension of the moment of inertia is kilogram meter square. Okay, so let's look how we can calculate moment of inertia. Given this is a plate, one thin plate. Okay, so it has a dimension of 6 and 2. So find the moment of inertia y of a uniform rectangular plate with mu. So this mu is the mass per area. So mass per area. This is the because this is a uniform rectangle. That means every part of it has the same mass. Okay. So why I put Iy? So Iy means rotation on around y-axis. That means, okay, so this is the plate. Okay, Iy means rotation at y-axis. Okay, for this problem. Okay, so we want to find the moment of inertia with respect to y-axis. So that's what I put Iy. Okay, so let's start by considering one strips of the plate which will be rotated around y-axis. Okay, you can see how rotate. Okay. So delta A, the strip, is equal to this length times this length, right? Height times width. Okay, because this is just a simple square, so we can readily understood that the area is just 2 times delta x. So this is relation that we can write. Okay, 2 times delta x, and then the strip, it has mass. Okay, this strip, it has mass. So the mass is equal to, because mu, remember again, equal to m over a. So m equal to mu a. So the mass depends on the area. So if we have big area, we have big mass. If we have a small area, we have a small mass. So one small strip here, this is equal to mu times delta A. So mu is 2 because this is 2. This is from the above, this relation we can put here. So we have 4 delta x. Okay, now we want to calculate, because every point it has its own inch in. Let's say in. So every point, so like this, every point it has their own moment of inertia. Now we want to sum them up. So we sum up from 0 to 6. So we sum all the strips. Okay, all the strips which consisted of all the particles on the plate. So we swipe it from 0 to 6. From 0 to 6, that means every strip. So this is the strips. So the strip, it has delta I. Okay, then we put this delta I. What is delta I? You see, delta I is m times d square. That means this m is just a small strip, so we put it delta m. This is small strip. X is the distance from here to here, x. So we have the distance, x squared. Okay, now we put here into this. So that's why we have 4dx times x squared. Okay. And then we can write, this is approximation. Now we want to make the exact value. So this is a limit of the x approaching 0. The summation from 0 to 6 of all these items. So for x squared delta r, sorry, I'll make a mistake. So it should not be delta x, it should be delta x still. Okay, now we can convert into the integration form. This is 4, we can put outside because it is just a constant. So x squared dx, now it becomes dx, not delta x. Now we can evaluate, and we get 288. The unit should be kilogram meter squared. Okay, kilogram meter squared. Alright, so this is for part x and y axis. So now if you are asked for x axis, that means if it is being rotated in this direction. This one is in y. So this is the axis. So this is the x-axis like this. So it is rotated down like this. So we consider a strip over here, which is delta y. So in similar way, you can compare between both of them. So this is also wrong. Okay, now you get 21.3. So you see there are different values. This is 288, this is 213. Okay, meaning that this plate resists to rotate in this direction rather than this direction. So if both are given the same torque, that means with the same force to rotate, so this will rotate slowly, but this one will rotate faster. So it means that moment of inertia depends on the axis of rotation. Okay? If the axis of rotation is here, we have to calculate differently. So that's why the moment of inertia depends on the axis of rotation. Okay, so that's all.